put it in yellow. I guess that's why I didn't see it. We're going to finish up the rest of the components today and then start on what they call practical circuits. The thing we're going to talk about inductors, and basically, an inductor is just can't be a straight piece of wire, but normally it's a coiled piece of wire or material. It could be air or some form of iron or ferrite. Most of the inductors and radios that you see today are wound on toroid made out of ferrite because it's
kind of permeability.
Kind of an inverse thing of least resistance to the magnetic flux. So if you have a magnetic material like iron or ferrite, which is iron oxide type thing, they concentrate the magnetic lines of flux in that material. So if you wind a coil around it, either a rod or a toroid, all the magnetic lines of flux is concentrated within that. So in the case of a toroid, you don't see any external magnetic lines. So you can have them adjacent to one another and you don't have any magnetic coupling, where you would in like an air core coil or iron like transformer. And we'll get into transformers a little bit, then some piezoelectric devices, which are quartz crystals that exhibit the property of you apply a potential to it, it will cause it to bend. So you can make it oscillate at a resonant frequency. That's what you normally use for frequency control in radios and any other equipment that needs to control a signal, the frequency. So, like I said, you have two kinds. You have solenoids, which is just a linear coil, and a toroid, which is like a donut. In those cases, there's just wire wrapped around it with a number of turns. The inductance increases with the number of turns and the area within the turn. So the basic inductance formula is there's permeability constant, the area times the number of turns. Like I said, most of them today are ferrite material and different kinds of mixing with different compounds that exhibit different characteristics of frequency. In some cases, you find out iron. It has some advantages, but in most cases, you're going to see ferrite. And the other advantage for the toroid is it tastes like a face. So it's a solenoid. Example one, showing all the magnetic lines of force being concentrated within that Not Bravo, because it's just the opposite. It inhibits the transfer. Back forward. What material properties determine the inductance of an inductor? Constant permeability, which is how well it how well it concentrates the magnetic line support. And all of those materials tend to be some version of iron. It's one of the few ferromagnetic materials. Mentioned sometimes use powder iron cores, particularly for high current devices, some transformers, because their permeability doesn't change with as much with temperature. As you get more and more power, you get heating in the core material. And in the case of ferrite core, if you get it up to the Curie temperature, it never recovers. So you can actually, and in some cases, they've been known to explode. Curie, Madam Curie, one of the things she's named for. But as its temperature increases in the ferrite, permeability goes down, and it gets to a certain point where it will not recover. You've ruined it, or in some cases, blown it up. As much. Right. That's why you use it in high power situation. But it doesn't have as much, it's lower permeability, it doesn't have as much inductance per turn. That's why you use ferrites, because you can have a smaller inductance. Not much higher permeability. Pictures of some of the clip-on ferrites, which you can use for EMI suppression. If you can also get cables built. You've seen them, USB cables and others you can buy with those already installed on them, or you can get these clip-on do it yourself. It helps eliminate RFI that may be running around in your shaft. You can't really have too many ferrite beads or clip-ons. Anything that's got a clip-on. Well, any of your audio type stuff, microphone cables, USB cables, the USB cables you buy with those ferrites on them cost quite a bit more. So which of the following materials has the highest temperature stability of its magnetic characteristics? We didn't talk about brass. Brass is sometimes used in inductors to actually decrease the permeability. Used to use brass old-fashioned coils and radios. You screw a brass plug on. Well, to control the inductance of it, but it reduces the permeability, so it lessens the inductance. How do ferrite powder iron hair for use in an inductor core. Pretty wordy.
I would think
What devices are commonly used as VHF, UHF parasitic suppressors? Input and output terminals of a transistor, high frequency amp. One of the things you have to watch for is saturation of the core. The actual volume of the core determines how much power that device can take. The smaller the volume for a given power, the more heat you're going to generate. Like I said, at a certain temperature, it doesn't work. Also, if you're using it, and we'll get into the transformer, if you're using it as a transformer where you're depending on coupling between the primary and secondary terms, as the permeability decreases, you get less coupling, so it affects the efficiency of the transformer. And it can also generate some harmonics. And then when you saturate it, effectively looks like it lost inductance because it's no longer acting like an inductor. It does up to a point that says, "Oh, quit, no more." If you look at it, this would be a normal sine wave. Starting to saturate, what you see is getting the saturation point sort of, it's not necessarily as sharp, but you see these drop. It gets worse the more it is. And every one of those kind of sharp turns is going to introduce harmonics of that signal, which you don't necessarily. Well, you have to look at it a little bit. What is inductor saturation? issues with inductors, similar with capacitors, is self-reference. So you have turns, so the wire is close together. You have effectively capacitance between the windings called interturn capacitance. So if you look at the circuit over here, see this capacitor is effectively there, even though it's not a physical capacitor. So you now have a parallel RC circuit, RLC circuit. So at a certain frequency, where the reactance of this inductor and the capacitor are equal, it's going to resonate. And it may or may not be at the point where you want it to resonate. It usually limits the upper frequency range you can do for a circuit, because when it, in the case of the parallel, when it starts to resonate, it becomes a very high, almost infinite impedance. And I said there was no formulas, but there's one down here. You remember that from last week, right? This guy. Okay, you can have variable inductors where you can vary the core material. Usually they call it a slug, and you have a way to kind of screw it in and out. You may have seen some mobile antennas on the back of a car, and has a big thing called a screwdriver, and that actually one of them has a motor and can change the core and effectively change the inductance or loading to make it appear longer or shorter than what band is trying to operate. And like I said before, brass decreases the inductance where ferrite and iron, powdered iron increase. What type of material decreases inductance and turns it into a coil? Transformers. Okay, so we have conductors close enough together that you have magnetic or wind them on the same. But that will create a current voltage. Secondary winding sees that magnetic field, and that generates a current. And according to Lenz's law, it's going to generate a voltage, a magnetic field opposing the other. Can't find my magnet, but I can demo Lenz's law. Where we have a super magnet, PCP, generating the magnetic field is generating current in that copper pipe, and that current in the copper pipe is generating a magnetic field that's opposing the magnetic field of the magnet. real world, it doesn't stop it forever, so it goes very slow. In the transformer, the voltage between the primary and secondary is proportional to the temperature. So if I have a primary with one turn, secondary with if I apply 1 volt on the primary, I see a 2 volt. Find out input and output. That would give me a 50 to 200 ohm impedance transformation. I could match that antenna, but they probably have more than 1 turn or 2 turns to get a better magnetic complex. So we're not there yet, but we will be. We talked a little bit about magnetizing current, and there is some hysteresis with it, because it takes a certain amount of magnetizing current to start creating a magnetic field. So when it releases it, you get a little bit of different path that's called hysteresis. So there's going in and coming out, but not the same. Did you talk about the generator? Okay. So one of the main uses for transformers besides power, if you see a power supply, is to mask impedances like for antennas. And again, you need to make sure that you're not saturating the core. So if you want to run 1.5 kilowatts, you need to make sure that you've got a sufficiently sized core material in that magic transformer. Or you might see one of those things blow up. And like I said, get into saturation, start getting the third, fifth order harmonic. For that, you don't have any comfort. This is another picture of what the input and output currents look like due to the magnetization. So you have a little bit of non-linearity there. So what is the current that flows in the primary winding of the transformer? No load. That's very right. So there's no load, so it's not delivering any power, but it's still consuming. Okay. You can use iron as well as ferrites. And normally, I guess until recently, almost all power transformers made with iron core. And they make it in very thin laminations that are coated so they're insulated. So that instead of having large, because you have the magnetic field, you actually generate current within that arm core, or eddy currents, and they can become quite large depending on the mass of the core. If you break it up into these little thin laminations, it forces these thin layers, so it greatly reduces the amount of eddy current. A lot of the bigger power transformers today are actually done for showing if you didn't have any laminations, then you get this large current flowing there. Where with the laminations, you get a lot of small eddy current. Wire cords and inductors are sometimes constructed of thin layers. Okay, piezoelectric devices. They discovered that quartz crystals, primarily quartz is used, but maybe
Robert? Robert? What is the difference between this type of piezoelectric crystal, as an oscillator or a filter, and then the type that heat or cool? There are some low efficiency devices that are used as refrigerators and heaters. You can keep something warm or keep something cool using a piezoelectric something or other. I can't remember what it is exactly, but it's basically a piezoelectric device. Now, this apparently is a piezoelectric crystal dealing with, RF frequency or audio frequency or something like that. So I'm not sure. Well, I'm curious, what might the difference be?
You're right. Very little latency. Takes a lot of power to cool something. But yeah, it's totally different. Right. Yeah, that's regular piezo. You hit it with a shock, and it will create a fairly high voltage. So it works both ways. I mean, you apply voltage, if you hit it, it will apply voltage. Or you bend it. And they use it in string cases where you can put it where it's either in torsion or bending, and it produces a voltage proportional to that. So you can measure bending and strength. But if we don't do that in radios, we just use it as an oscillator.
Thank you.
Okay. The main thing to remember is this last one. This long sentence where a crystal is a most and loss resistance in series, all in parallel with a shunt capacitor representing electrode stray capacitor, equivalent circuit for a circuit. So the motional capacitor is the spring portion of the crystal. The fact that it is flexible and that it does flex, and then it has mass. So we'll see over here what they describe. You've got series resistance, motional capacitance, some inductance, and this shunt capacitor. I point that out. It's a test question. Remember, it'd be the only one with that one with motional capacitance. Yeah. What is piezoelectricity? Which of the following is an aspect of the piezoelectric? What is the equivalent circuit of a quartz crystal? Reword the